Yeah, so this is joint work that I did with my advisor, Reid Simmons, who unfortunately couldn't come to the conference. So motivation behind using this multi-model approach comes from transport robots and them navigating these very non-uniform environments. So for an automatic warehouse robot, there's might be these open hallways that it often encounters, but at the same time there might be different environments where there's overhangs and walkways for people where the height is important to consider when planning, or you'll have different flooring such as carpet, where you can have different areas of the space that can be both cluttered and very open. So for warehouse environments that are not tailored for the robot, it's very important to kind of consider what would you do in these non-uniform environments. Similarly, for hospital robots, time is very important for time-sensitive medications that need to be transported through the hospital, or trailers that are taking linens to different locations. And for these robots to be robust is also a very important factor because you incur a large cost when you have people trying to assist the robot in scenarios where it might not be progressing in its task, whether that's robots that are being teleoperated, where there's a high cost for the teleoperator, or hospital workers. So these environments are also can be very non-uniform. So maybe on a typical day, the hallways are always open, but depending on the load of patients and different times of the day, you can have these different cluttered areas or these automatic swinging doors where people are coming in and out. And even as an anecdote, we found that when these robots go around and seem that they're having trouble in different locations, workers will often take it upon themselves to assist the robot, and this can be bad if the robot is not doing things quickly, where even in the most extreme case, robots have been turned off and thrown in utility closets. So that was kind of a bad scenario for trying to figure out why the robot went offline. So the idea is that by leveraging these multiple models, we can balance between this efficient planning time and execution reliability, this execution success. So simpler models might be used more often. They generalize over more environments, and so they can be used a lot in the open regions, or just maybe that's the go-to model that is always used. But there's these cases where you might have these complex locales where a more complicated model is important. So more succinctly, simple models save plan time, complex models give you sort of this execution robustness, and so by switching between them, you get the robustness of these high fidelity plans that are trying to only use these more focused models, hopefully only when necessary, so that you're also saving on plan time. So for generating a motion plan, this is the domain that we're working in. We're working in continuous space. We're using a sample-based motion planner, the RRT planner. The description of sort of where this model comes from is the first two boxes. So our models usually have definition of state. The lower models that are purely geometric might not have these motion equations, that describe the actions between them. But as you can imagine, these models can increase in complexity. So you can start out with purely geometric models and move into kinematic models and models that consider dynamic. So you're talking about 2D planar motions, slopes, coefficient of frictions of the terrain, and things like that allow you to sort of think about what are possible models that you'll use most often and others that might be good to have around in case the robot runs into these unexpected situations or these non-uniform environments. So models can overlap each other, they can be completely encompassed in each other, and model by definition is an approximation. So as you approximate more closely to the real world, you can imagine that the highest possible model is intractable. So this idea of using multiple models is potentially also a way to get closer to approximating the intractable sort of real world environment. So our models, again, they conclude states and controls, and we're using ordinary differential equations to define the mapping between them, which we use in our propagation functions for our sample-based planner. So the models that I was using in this work describing a differential drive robot in the gazebo simulation with a trailer. And so this is an example of a model graph where we just have a breakup of these different models where the XY path is a geometric path that's moving in these straight line motions. The extra theta variable is used to describe the position of the trailer, and then it can get up into velocities and accelerations and then grow from there. So there are some assumptions that we make that we refer to in the paper, but all of them have like a common ancestor, so we expect the graph to sort of end in one common node for this PlanTime approach. So to give a better context of how this looks in a planning and a navigation state, so our XY model generates these straight line paths, which we then translate to be execution feasible on the robot, but having it do turn in place actions. So this is an example of kind of how it would look, this path being generated purely just in this model. And now if we're considering the trailer, you'll tend to get paths that might go more around all of the obstacles. So here the trailer is sort of the pink arrow that's following behind the robot. This is just a kinematic model. And then if we're taking into account velocity and acceleration inputs, you'll get paths where the robot will actually kind of slow down and speed up as it's going from the start to the goal. So it's considering these additional control variables. So to better describe the algorithm, the PlanTime algorithm that we're using to determine when to switch, first what we do is we generate a motion plan in sort of the lowest applicable model for your environment. So this is obviously going to be different depending on what environment you're using. So for this simpler example, it's the XY model. And then this model is actually translated into the highest model, and then we can collision check along that highest model path using similar propagation functions that were used when generating the plan to determine where we think a collision might occur. So here's like where the infeasibility might be. So now in the highest model, we're actually considering the trailer. We're moving the robot along the path with those controls, and maybe we see that we think there is a collision between waypoints 4 and waypoints 5. So then the next step is that if the path is not completely clear, is that to actually go and select a model using our model graph to replan with. And this is a similar thing where we take the partial path that we saw had failed, and then we simulate in that particular model using the propagation function within the planner. And if the robot successfully goes through that path, we assume that no additional information was gained from that model. So we're currently doing just a breadth first search through the graph. So now maybe it will go to XY theta. Again, nothing was detected. And so maybe the higher model that is using the trailer has seen that there's a collision, which we hypothesize is saying, hey, this model is including some information that we think is relevant. And so that's the model that we're going to be using for replanning. And in this particular case, we effectively can skip levels of the graph. So we went from XY all the way up to the trailer model. And so it kind of will automatically detect which model to use next. So then when we choose the model for replanning this partial path where we determined this infeasibility, we actually use a multi-tree replanning approach. And this is to maintain probabilistic completeness guarantees. So the idea is we start out with a nominal global path that can actually be a multi-model path on its own. We saw that there was an infeasibility between waypoints 4 and 5. So then we replan to the different waypoint goals along that nominal path as if they were intermediate goals. So we're actually planning towards a goal set. And then we also, because we don't know exactly where the infeasibility could have occurred, replan where each of the initial start nodes are separate replanning trees. So now we're growing a separate tree from waypoint 4 to all of the intermediate goals. And then from waypoint 3, one is growing from all of those intermediate goals, and so on and so forth. And we're actually choosing to expand which tree at which time step based on the probability of an inverse distance metric. And this was just to try to keep these partial paths as close to where we thought those infeasibilities were to help speed up things by reusing old parts of the initial path. So the idea is that if in this particular case the tree from waypoint 3 actually connected initially with waypoint 6, then we would take that partial path and remerge it back into our initial global path. And then again, the algorithm would go, translate that into the highest model, check that path. If that path is seen to not have any infeasibilities, it will be sent on to the robot for execution. So the environment that we were working with was to try to simulate some of the things that, for the hospital case. So here we have a bunch of different gurneys that are kind of close together. And so the idea, again, for a very simple example, is that in this case there was a collision found once the robot was rounding the corner that was not seen in the lowest path, and then it was replanned in XY theta to smooth it out, and then once it's sent to the robot for execution, on the right side it's the robot in the simulator, the gazebo simulator, following that path through. So in the results for our gurney world, actually since the paper has been published, we've been able to improve on this false positive rate. So I wanted to touch on that. As a good metric for determining this sort of highest model collision checker and how well it's comparing to the execution for the robot, is we really took a look at the false positive and false negative rates, where false positive would be I'm checking in the highest model, I think that there is a collision, but if that path was actually sent and executed on the robot would have executed successfully. The false negative is the opposite case, where you think that the path being checked is actually free, but when put on the robot collides, which arguably might be worse. So if you eliminate these false negative cases, if any exist, you increase success rates. And if you eliminate the false positive cases, then you're minimizing the plan time better. So we believe that the better that these can be matched by matching sort of how the underlying controller is actually doing the waypoint following, similarly to the planning checker, which for the plan time, that we will actually be able to balance these better for the switching. So something to note for this particular environment is that we found that the trailer theta model was most important. So the first group of runs are each model, we did single runs of 20 RRTs, choosing the shortest length path to try to maintain consistency. And we did 100 runs total of these 20 individual runs to see success and plan time rates. Success rates were a lot higher when you're thinking of the trailer model, but it also shows that there isn't a single best model to use, that the models really has to be appropriate for that current environment. So our switching results were able to get lower plan times because of the false positive rate. But we did have false negative rates by not really being able to model the trailer dynamics as well as we'd like, because really you'd like to take into account the mass of the trailer, because it really was affecting the swing depending on how the robot was accelerating through the turns. So we were just using a purely kinematic trailer model here. So it's kind of my inability to model it as well. So it suggests that higher models would be useful in that domain. So this domain, the robot would approach 2 meters from the door would automatically swing open, and then the robot would go through the door, and then the doors would automatically close. So this is an example of the highest model where the robot actually slows down, waits for the doors to open, and goes through for the path that's shown. Those little boxes are actually how we were collision checking. We were doing it by doing a time step, different time steps where it was open, where the full open and closing of the robot would be collision checked, and then where it was closed. So you could see that because that's a continuous variable, we could also eliminate our false positive rates if we were more discretized with how we were time checking the doors as well. So it's being a little overly conservative, if that makes sense. So for here, though, because we improved some of how the highest model checker is comparing to the controller, we were also able to get slightly better planning times for the switching than what was shown in the paper since the paper's publication. And velocity was very important for this domain, as well as seeing that having to collision check additionally the trailer going through the doors takes considerably a lot more time. So in conclusion, we produced these single mix model plans where we're trying to really choose the most applicable model based on the environment and the current spot of the robot's task, and that we're hoping to achieve this idea where the robot is both smart and fast for these different domains. So I guess I can do it. That was fast.
Questions? Yes, please. So here talking about plan feasibility, how would this change if you want to talk about trying to optimize for some metric, say execution time?
Yeah, so that would be the interleaving the planning with the execution and trying to think about how
even arguing about optimal planners or asymptotically optimal planners. So the problem is that optimizing for the geometric path would get you very close to the obstacles.
Right.
And that is totally different from what the
maybe what a higher model path would take.
do.
Yeah.
So how would you take that? Have you have any thoughts on that?
So it actually was interesting because the lower model is seeding kind of where the higher paths would go, and in some cases the higher paths might, very infrequently go to a location the lower path is. And so that was something that we saw when going through that narrow hallway when using an RRT. When you're replanning in the narrow hallway, it takes like a very long time, and the higher model paths tend to always sort of circumvent it, but now I was kind of forcing a lot of them to go through that, which happened with that harder domain, because before, my gurneys were actually not nearly as close, which was nice. Yeah, no, it's a good consideration. I think the idea is that you could incorporate like different kinds of models, the learned models and more optimal models for those particular tasks. But I think in practice, you'd want a model that is successful the majority of the time. So here we are purposely using ones that were not as great to sort of show the efficacy of the algorithm. But you would want like 98% of the time that the model you choose is really good. And then in very rare cases, maybe you have like one that's like helpful in that particular instance that you wouldn't think of. So I would say using the optimal one to begin with is probably a good start. Yeah.
Alan, last question.
So I saw in your results there was a couple of percentage points between sort of your best model success and the switching.
Yeah.
Could you just maybe give a little intuition? Is that because...
For which world? Like why it didn't match the highest model?
Yeah, is it just starting out, is it the reuse of the previous plans and seeding from those?
Yeah, so from watching runs for the gurney world in particular, the trailer sort of really made things interesting, and kind of the example that I was giving here is that a lot of my lower models were going through that hallway. And the trailer, if it's not kind of lined up properly, might have additional swing. And so depending on sort of where that collision took place and how those replans happened with the trees, if I was accelerating in, very slowly, and the trailer would actually keep hanging low and clip something versus turning very quickly. So the idea is that the false negative rate existed, and looking at how I could minimize that false negative rate to increase the success. So never have these cases where I have a path and then I replanned with some of the models but not the acceleration model because my checker said that was good enough, sent it to the robot, and now the robot is trying to use the underlying controller, which arguably could have been better, maybe to follow the paths better, and then created this swing that gave me this 1 or 2 extra cases where it would hit where it wouldn't have expected it to. So that's for that particular case. For the swing, for the door world, there was kind of something similar depending on how it was approaching the door, but also how I was discretizing the time steps for collision checking was another factor that could be improved for sure.
Now we have a coffee break for more questions, but let's thank the speakers again.